嗨，
喂，玉霞，你能听到吗？
嗯，可以，可以，你们可以听到我这边吗？嗯，我有没有看到 sharing 啊？哦，可以了。嗯，可以了吗？等一下。 No. Mm. 你可以了。
Two. There's, yeah, they've got audio coming in there, so that's good. Yep, one, two, two, two. Yep, one, two.
现在好像能听到一点。
I can hear you.
Testing. Yeah, if they want to have a chat to us as well, then we can test that their levels are coming back into the room.
You can type.
Hello，
Hi.
我们这应该可以，这个应该可以。不，他能说句话，这样我们听。
玉霞，Can you hear us? Can you test the microphone?
Yes, I can hear you. Can you hear me? Can you hear
他
me?
能说吗？好像说不了了。他好像在说，但是我这边没有开声音。不，他这个应该在屋里，他有。
我在说。
不是我想说的说，
那有问题。听不到。
听不到。你们听不到吗？OK。这个。
这边看一下可能会。
That would be cool.
设置后面那个，反正正在看那个完全的调整设置。玉霞，请再说一句话。
你们可以听到吗？Hi。
好，谢谢。
可以吗？
听不到。Sorry, can you say something again?
Yeah. Can you hear me?
玉霞。
Yes. Yes. Can you hear me?
We're still sitting up. You guys will be. That's an issue that Yuxia, can you say something? Sorry.
Yes,
Can she hear?
I'm here. Can you hear me?
Sorry, we're having some technical difficulties, so we should be starting shortly.
Yuxia, can you say something again? Sorry.
Yes, can you hear me? I'm here.
Sorry, it still doesn't work.
Uh,
No, I think what will happen is that will transfer, this would be in draft, that will be done today.
对，就是online里面他们也放不出来。对，对，蛮好的。是吧？没有，好，提前培训好。那你不耽误事儿。We can try. We can try to speak. This we won't be able to. Yes. Sorry about this. 第三段的
Okay, thank you for the waiting. All right. Okay, so let's get started. So we are very honored to have this tutorial at WWW 2025. So our topic is on few short learning on graphs, from meta learning to LLM empowered pre-training and beyond. So this tutorial is jointly organized by myself, Yuan Fang, Yuxia Wu, Xin Tongyu, and Professor Shirui Pan. So myself, Yuxia Wu, and Xin Tongyu are from Singapore Management University. Right, so I'm an assistant professor at the School of Computing and Information System, and Yuxia and Xin Tong are postdoctoral researchers. And Professor Shirui Pan is an ARC Future Fellow with the School of Information and Communication Technology, Griffith University. His research focuses on AI and machine learning with significant contributions to graph machine learning methods. So this tutorial actually is based on the following survey paper, and we also have a corresponding GitHub repo. So if you go to this repo, the slides of today's tutorial is also on this repo. And some of the material of this tutorial is also based on this survey on graph foundation models, concepts, opportunities, and challenges, which was recently accepted to PAMI 2000, PAMI, yeah. And it also has a corresponding repo. All right, so this is what we are going to do today. So we are having a bit of delay, but I think we can probably catch up later. So Professor Pan will give an introduction on graph and its applications. Then followed by I will be giving an overview on what kind of problems and applications we are dealing with in graph few short learning, right? Then followed by Yuxia Wu will be giving a talk on meta learning based approach for few short learning, right? Then we would have the coffee break. After the coffee break, we will be starting on pre-training approaches for few short learning. But for the pre-training approaches, it's further divided into pre-LLM and the LLM era. Okay, in the end, I will conclude with future research directions and question answering. Right, Professor Shi. Professor Tan, sorry.
Okay, good morning, everyone. So I will start by grounding ourselves on graphs. So what are graphs and why graphs are really important? So we know that, so nowadays we got the text data, we got the image data, we got the audio data. Actually, graphs is another really important data modality in our real life. Graph can be seen in many applications, including the social network. For instance, we got the Facebook, we got the LinkedIn, and we got X, right? So in this kind of social networks, nodes are the users and friendships are X. And also in recommendation systems, for instance, in Netflix, we got a set of movies and we have many users, and the task is to recommend the movies to the users, right? So basically we can model the users as well as the movies as the nodes and their interaction as edges. And the task is to predict the interaction between the users and movies as well as the rating, right? And also in the biological domain, we have many molecules or proteins, and many of these molecules can be represented as graphs with the atoms as the nodes and the edges as the chemical bond, right? So, and we can predict the property of this molecule, or we can predict the interaction between the proteins. So graphs are a data modality, and is also a very important tool to model the complex relations between the entities. So to deal with this kind of graph data, so recently a lot of graph learning approach have been developed, and this approach typically follows an end-to-end learning paradise. By end-to-end, we mean that actually we are not doing the manual feature engineering. Actually, we directly learn the representation from the graph data, as well as do the downstream task, for instance, do the prediction of the molecular, or to do the low-level classifications. And in the graph learning, typically there are two very important approaches. The first one is graph neural networks. So graph neural networks become very popular since 2011, and the graph convolution network was developed at that time. And in graph neural network, typically they use a message passing paradigm and to learn the representation for every single node, every single edge, and all, as well as the graphs. So for instance, we can aggregate the information from the neighbors to a target node, and then we gradually update the node representation. And also at the same time, graph transformers was developed, and it was very popular. We know that transformer is very important architecture, which is widely used in natural language processing and also vision. And transformer is also the building block for current generative AI techniques such as ChatGPT, right? Graph transformer has been also used in the graph domains. So in transformer, we aim to learn the attention score for every single node to a target node. So if we go back into the detailed graph neural networks, we know that, so as we mentioned, graph neural network follows a message passing framework. In the message passing, the key is to learn the representation of every single node, right? So in this paradigm, so we will aggregate information from the neighbors, the direct neighbors, to a target node, and then we iteratively update all the representation of all the nodes. And then we step multiple layers, for instance, a graph convolution layer or graph attention layer. Eventually, we can get embedded for every single node. And if we are focused on the edge level, we can get the representation for every single edge. And if we are focusing on the graph level representation, we can also pull in the representation and then get the representation for the graph level. And eventually, we can do all sorts of downstream tasks. And another architecture is called graph attention network, which is also very popular and very important. Graph attention network actually improve graph convolution network by learning the weight or the importance score of the neighbors to the target node. So in graph convolution network GCN, so the weight of the neighbors are the same and predefined. But in GAT, graph attention network, the weight will be automatically learned by an attention mechanism. So that's a brief review of the graph neural networks. And also we got the transformers, right? So why we already have graph GCN or GAT? Why do we still have graph transformers? So in the graph neural networks, typically we only aggregate information from the direct neighbors, right? So it may ignore the global information. For instance, if the node is quite distant from the target node, so its information may be ignored. So in transformer, actually we calculate the score or the attention score from every single node, so which enable us to capture the long range dependency. And transformer have been widely used in the different kind of graph data, including the homogeneous graph where all the nodes have the same time, and also heterogeneous graph, for instance, the node may have different times and the relation may have different time. And here are two representative research on graph transformers, including the GTN and HGT. So in the GTN, for instance, they learn the importance of the meta pass automatically and then learn the adjacent matrix, which is very important for the graph learning, and then aggregate attention the score for different adjacent matrices. And the HGT is designed for heterogeneous graph where different nodes have different times. For instance, in the academic network, we got the user we got the conference and we got the paper. So these nodes may have different types. So, in previous GNN research, typically actually we require that the user label quite a lot of data, but sometimes it's not practical in many applications, particularly in the biological domain. For instance, if you like to understand the property of molecular, right, you may need to do a lot of web experiments. So it's costly and also takes time. So few-shot learning actually can adjust this kind of challenges. So it can adjust the label scarcity. So if you only have a few label data, actually we can apply the few-shot learning to this problem. And also in traditional graph learning, so if you like to get a very good performance, you may need to have a very good graph structure. But in many applications, the graph is noisy, it's very sparse, so we have the structure scarcity problems, and few-shot learning can also address these problems. But so how few-shot learning can address these challenges? So basically, as will be discussed by our colleague later, so there are different kinds of approaches here, including the meta-learning approaches and pre-training approaches, as well as the hybrid approaches. So for few-shot learning, so the key is that we try to learn the pride from, for instance, a set of meta data or meta tasks, or we try to learn the prior knowledge from some pre-trained data set. So for meta learning, for instance, we can enrich the structure of the data. So and we can also think about how to develop adaptation-based enhancement approaches for few-shot learning, and also for pre-training, because we will pre-train and, for instance, graph encoder from a set of text tasks, and then we can consider how to fine-tune the graph encoder as well. How to fine-tune the graph encoder for the adaptation for the future tasks, and also we can develop some parameter efficient adaptation approaches. So a little bit of review about these three approaches, and we will give more detail later. So meta-learning approach basically derive the prime knowledge from a series of meta-training tasks. And for pre-training methods, so it utilizes unlabeled data to optimize self-supervised pre-text tasks. And also it will employ fine-tuning or parameter-efficient adaptation approach. And the hybrid approach basically integrate both these two different paradigms. So this is a little bit of introduction of the problem and also the approaches here. And next, Professor Fang will introduce the problems and applications. Thank you.
Okay, thank you, Professor Pan, for the great introduction. So in the following maybe half an hour, I will be talk about what kind of problems and applications in graph few-shot learning. Okay, so first we try to derive a categorization of the few-shot problems. So we broadly categorize few-shot learning problems into two categories. One is we call label scarcity. So we don't have enough label data. The second category is what we call the structure scarcity, where there isn't enough structural connections in the graph. The graph is sparse, especially for some of the nodes. So in label scarcity problem, we further studied two kind of scenarios. The first is a class-based label scarcity, right? So in a typical setting, we can have a base class. Okay, we can have a set of base class for model training. So this base class is actually an existing set of classes that's available with a lot of label data. Then we also have a set of new classes. Okay, the new classes is for the actually for the testing. So the total set of class is the base class together with the new class, and there isn't any overlap between the base class and new class. So when we talk about label scarcity, the label scarcity could happen in either the base class or the new classes or both. So let's consider this scenario. So one scenario is that we have a lot of labeled base classes, right? So we have enough label data, but for the new classes, we do not have sufficient label data, or maybe only a few label data for each new class. So the goal here is how to learn prior knowledge from the labeled base classes. Then the prior knowledge can be transferred to the new classes with only a few label data, right? So these are typically we can adopt a meta-learning based approach, which we will also introduce the details later. But basically, the new classes also has two parts. One is a support set. The support set contains label data from the new classes, but typically this support set is very small. Okay, each class maybe you only have one example that's called one-shot learning, or you have a few examples that's called few-shot learning. Then it also has a query set. The query set contains unlabeled data for the new classes, which you actually do the inference, do the testing on the unlabeled data. Okay, but the problem of this setting is that you still heavily rely on abundant label data. You need a large number of base classes, right? So although it can deal with new classes with very few label, but you still need to have a separate base classes with a lot of label data. So this leads to the second scenario, right? So what if we have label scarcity in base classes as well? Or in an extreme case, we do not have any labeled class. We do not have any labeled base class. So in that case, meta-learning approach doesn't work here, right? So instead, we can use self-supervised methods. So these self-supervised methods basically is use some kind of self-supervision. It does not need labeled base classes, but we have a few self-supervised pretext tasks that we can pre-train some graph encoders, right? Then the pre-trained graph encoder can be adapted to the new class through some common techniques like fine-tuning. Okay, and there could also be cases where we have label scarcity in both base classes and new classes, right? So in that case, we are still going to use self-supervised learning to pre-train a graph encoder, which doesn't require any labeled base classes. But for the new classes, fine-tuning, we can still do fine-tuning, but we may need to look at parameter efficient fine-tuning approaches. Right? Otherwise, if you're fine-tuning a lot of parameters, it's going to require more label data as well, right? But if your new classes have only a few label data, then traditional fine-tuning that updates all the parameters is not going to work. So we are going to look at parameter efficient methods. Okay, so I talked about the class-based label scarcity, but if we look at the problem setting, we can also look at the label scarcity from the instance level. So at which level of the instance we have a label scarcity. So basically in a graph, we have node level, edge level, and the graph level, right? So for node level, we have typical application domain like we have an academic network, right? Or we have a social network. We have users in the social network. We need to classify the users, right? Or classify the post in a social network. For edge level, we have applications like predicting drug-drug interaction, right? Or in e-commerce recommendation system, we try to predict the interactions between users and items. Right? And finally, on graph level, we are looking at whole graphs, for example, a molecular graph or a protein graph. We're trying to classify this protein, whether it satisfies certain property or whether it is belong to a certain class. Okay, so for node level label scarcity, I have briefly mentioned just now, but these are different examples. right? So I think most related to the web conference is probably the social network and the recommender systems, right? In a social network, we have different users, right? Different users can have different, like they upload different photos, different videos, and so on. You can actually try to classify these users as well as their photos. In recommendation system, right? Although recommendation system is mainly to predict the interaction between users, but sometimes we also need to know the category of the users or the category of the products so that we can promote these categories better, right? So in those cases, we need to classify the products, right? So in these cases, what if we have less label data? Especially with privacy issues in social network and in recommender systems, the user profile is very limited and considered as private. So we couldn't have a lot of label data. And for edge level label scarcity, in graphs like drug-drug interaction, right? Or we are trying to predict multimer structure, or in knowledge graph, we are trying to predict the relationship between different nodes, right? And of course, in e-commerce, we are trying to see which user buys which item. So in these cases, in some cases, the interactions, the edge level interaction could also be quite scarce, right? We can't afford to have a lot of such labels for the edge. So in these cases, we may need to have to deal with this edge level label scarcity. And finally, on graph level label scarcity. So basically in graph level tasks, we are trying to predict the properties or categories for the subgraphs or the whole graph, but we also have limited label data. For example, one example is in social network, right? In social network, like Reddit, you can actually form a graph for each thread. So in each thread, you have different people discussing have different comments. If you link all these comments and posts, they actually become a thread graph, right? So each thread has a label, like which topic of the thread is about or which category this thread is about. So this is a graph classification problem. Then of course in molecular graph, given a molecule, does it have a certain property, right? For example, is it soluble in water or is it has any toxicity? And of course, in protein prediction, what is the function of the protein and so on. So all these, whether in social network or in biomedical applications, in many cases, we don't have enough label data, right? So how do we deal with this? Okay, then we have talked about the label scarcity problem. The second branch is structure scarcity. Right, so structure scarcity is is not about the label of the nodes or edges, but about the distribution of the structural connections. Okay, one common example is we have a long tail distribution. In many graphs, the node degree follow a power law, means that only a few nodes have many connections, but majority of the nodes have very few connections. Then for these majority nodes, because they have very few connections, when you apply, for example, graph neural network, using a message passing architecture, those nodes with very few connections, they can't benefit from the message passing process. And in some cases, like in recommendation, we have this cold start problem. Cold start problem is also a structure scarcity, right? Because in recommendation scenarios, some users, they are new users, so they haven't bought any products before, right? So their interactions with existing products are very limited. So these interactions are basically structural connectivities in the graph. So cold start problem is trying to look at how we can learn good representations for nodes with very few or even no connections. Okay, so let me talk a bit more about the long-tailed distribution. right? So let's focus on this the first two little small graph here. So we can see that if we rank the nodes by degree, right, you can see that the degree distribution follows the power law distribution. So it means only very few nodes at this part, maybe the top 5% nodes, they have high degree, but the majority of the nodes have low degree. So what's the implication of this? It will actually directly impact your performance if you are trying to do some learning tasks. Like for example, if you are trying to do node classification, you can see that in the second figure here, we are ordering the node by the node degree. So different group have different degree, and it's a increasing degree. And you can see that as the node degree increase, the performance, the classification accuracy on these nodes also increases. So the reason is quite intuitive, right? For nodes with high degree, they have a lot of connectivity. So when you are doing applying a graph neural network, when during the message passing, a lot of information from related nodes can be propagated to the nodes, right? So they have good representations. But on the other hand, when you have a low node degree, let's say you only have one neighbors or a few neighbors, then when you are doing message passing, a very few information can be propagated to you, right? And if some of the neighbors are noisy, then your representation would be not well learned, right? So the node degree, the structural richness actually has a direct correlation with the performance of the classification. And if we look at the other nodes, the other data sets, they typically follow similar style, all right? The similar distribution on the node degree. So so how we actually deal with this? So this is actually a case of imbalanced node classification. So typically in a graph, we can divide the nodes into high degree nodes or low degree nodes. So for high degree nodes, we may learn very good representation, but for low degree nodes, we are not good at them. So how do we do it? How do we solve this problem? So one intuition is we can try to learn some prior information on high degree node and then transfer the information to the low degree nodes to help the low degree nodes to learn better. Okay. Then for the cold start learning, cold start is a very important problem in recommendation, right? So for example, here we have a KDD Cup 2012, all right? So it's on search advertisements, all right? So it follows this 80-20 rule, all right, or the power law distribution. 5% of the advertisement actually accounted for over 80% of the samples, right? But 95% of that had a very small amount of data, right? So this 95% is actually the cold start problem. Okay, when we don't have a lot of data, what can we do, right? So so the idea is also similar. So we are trying to leverage those advertisements with a lot of with rich connections, right? And then try to transfer such knowledge to the tail advertisements with limited connections. Okay, so here is I'm going to give a overall taxonomy of our few shot learning techniques. Okay, then later on we will be delving into each approaches, right? So just a note is that the technique taxonomy is orthogonal to the problem taxonomy. So in the problem, we say there are structural scarcity and the label scarcity. And under the label scarcity, there are also different kind of label scarcity. And under techniques, we have meta-learning based approaches, pre-training approaches, and the hybrid approaches. But it's not saying that certain approaches can only apply to certain problems. They are orthogonal. So for example, meta-learning approach can be applied to solving node level label scarcity, but it can also be applied to solve structural level like cold start problem, right? So similarly for pre-training, whether it's a label scarcity or structural scarcity, pre-training can help in different ways, right? So under a meta-learning approach, we have a structure-based enhancement and adaptation-based enhancement. On the pre-training approach, we have we are going to talk about pre-training strategies, right? Then followed by how we can do adaptation through traditional fine-tuning and then parameter efficient fine-tuning. And we are also going to talk about how we can leverage large language model to help with graph learning, right? And finally, the hybrid approach is actually combining both meta learning and pre-training approaches. Okay, I think that the next part is we are going to start with meta learning approaches. So Yuxia is unfortunately she can't be here with us, so she will be deliver the talk online. So Yuxia, can you unmute and test?
Yes.
Okay.
Can you hear me?
Yeah, we can hear you. Is it loud enough? Can you maybe turn up the volume? Yuxia, can you maybe you start talking
Yes.
first? Let's see if it's loud enough.
Yes, is it okay? Right now. So, this volume. How about this volume?
Do we have a microphone that can?
I
Yep,
Okay.
just chat for longer.
Yuxia, you can keep talking.
yeah.
Oh, okay, I think it's better, right?
Okay.
Maybe you can share your screen so you can control the slide. Yeah.
Yes. Can you see my screen?
Yes, yeah.
So, can I start now?
Yes, yeah, you can.
Okay. Hi everyone, my name is Yuxia Wu. In this session, I will introduce the meta-learning techniques on graphs. Before that, I want to give a quick recap of standard meta-learning techniques. In this scenario, for example, in the MAML paradigm, we have training tasks, including the support site and query site for different base classes. And our goal is to learn a prior from the training task and then adapt to the testing task. So it can also called learn to learn. In graph domain, the standard meta-learning paradigm can be seen as this. We can give an example as a node classification. Here we have some base classes and we also have the novel classes. So the training paradigm on graphs, the meta training tasks are constructed from the base classes, and the meta task are constructed from the the query contains some novel classes, and all the support sites they have a label, and for the query site, only the query site in the meta train task have label. So the query site in of the meta task they have we have to predict the label of this kind of samples. Okay. However, in the the standard meta-learning approaches cannot be directly used on graph domain. So in the graph, we have two kind of methods, structure-based enhancement and adaptation-based enhancement for the meta-learning. For the structure-based enhancement, we have node level, edge level, and subgraph level enhancement methods. The first, I will introduce the node level enhancement. It means we want to differentiate the node weights in a task to reflect the varying structure importance. Here we can see that here is our training on the graph domain. We have meta training tasks. So for each node in the support site, we want to learn the node weights for different nodes to calculate the prototype. So we have a node evaluator. This node evaluator is to estimate the node importance scores for different nodes. So when we can compute the prototype vector, we can assign different weights for each node. So this is called node level enhancement on graphs. Here is another similar pipeline for node level enhancement, but it focuses on few-shot knowledge graph completion task. Here is an example. In knowledge graph, we have a query, includes the head node, tail node, and the relationship. And we also have some reference based on this kind of relations. So our task is to predict the tail node, given the query, the head node, and relationship. We want to predict the tail node NBA here. In this kind of knowledge graph completion task, we have only few short examples about this query. So in this paper, they have two attention modules. They want to learn adaptive entity representations and the reference representations. Here, the figure A is an adaptive neighbor encoder for entities. Our target node is beer gas, so we want to learn a better representation for beer gas. So we compute the attention based on this entity and other this entity, and this is the relationship we want to predict. So we have compute attention to learn the relationship of different relation, different of the target relation. So in the following parts, they also want to learn an adaptive reference representations using an attention module to learn the query and the reference in this part. So each reference they have got a weight beta to get the final score. In the following part, I will introduce some edge level enhancement methods. We know that the edge in the graph can provide more fine-grained information about the relationship of two nodes. In edge level enhancement, they usually leverage auxiliary information associated with edges. Here is an example of knowledge graph too. For this query, we have a head node and tail node. So the edge they provide semantic information of the relationship of the nodes. in this work, they built a matching network for the entities and the relations. We can see that this is an entity-aware score to compute the weight for our query entity and the entities in the reference. Note that we have many reference samples, so we can compute the entity-aware score based on the weight of different reference. And another line is the relation-aware score. We also want to learn the attention weight for different relation. So here is a relation representation network and use a convolution operation to compute the weight score of different relation. Yeah. Here is another edge level enhancement. They use a pass to capture the more fine-grained information about the two nodes. In this paper, they consider different kind of paths between the support node and the query node, and they also consider the hub nodes because here the hub nodes here it is some nodes with high network centrality score, such as the high degree of PageRank score. This kind of nodes they can capture the global information within this graph because it has many links to other node. So in this paper, when they choose the path, they choose different kind of paths. The first one is the path between the query between the query node and the support nodes. So they use this kind of path to conduct task level dependency. And another kind of path is the query node and the hub node. So this kind of path can capture the graph level dependency. So they built the two kind of dependency in the graph domain and use meta learning to do the task. It is a few-shot node classification task here. Here is another example of edge level enhancement. It considers the HIN, it means the heterogeneous information network. Here is an example. In this network, we have different nodes and edge, they belong to different type. We can see that we have the node, user node and movie, actor and director. So this kind of network called heterogeneous information network, heterogeneous graph. So in this paper, they want to capture the semantic information of the path. You can see that it's called the meta path. So the meta path is some predefined path. It can provide heterogeneous semantic relations. For example, the means the path from user to movie, and UMAM from user, movie, actor, and movie. So they define four kind of meta paths. So for the support side and query side, they extract the different kind of semantic meta paths. They call this semantic context. So our goal is to learn better user and item representation for COSTA recommendation domain. In this meta learning pipeline, for different meta paths, so we can learn the user's preference from different semantic. Another category is the subgraph level enhancement. In this kind of methods, they extract the query, the query set and the support set. They use a subgraph. We can see that the input is the subgraph. So for this kind of subgraph set, we can learn class prototype for different subgraph, and for the query node, we also expand the node to subgraph. So this is a classic subgraph level enhancement. Another paper, they consider the subgraph in knowledge graph. So they want to deal with the few shot out of graph link prediction task. This task is here is an example. We have some links. Is it called in graph? It means we have seen the node and the link. And our goal is to predict the links of unseen node. So here, the right line, they are unseen to unseen node. So this is the task of this work. So they built a meta learning framework. So the meta training, they also have some links between seen to unseen and unseen to seen. But during the construction, they consider the neighbors of the target node. They consider the one-hop neighbors, so it can construct a subgraph for the support side and the query side. This is another interesting work. They consider the node degree. From this figure, we can see that the node degree shows a long tail distribution. So we have many nodes with high degree, but the nodes with low degree, they have a few links with other nodes. So how to learn how to learn a better embedding for the tail nodes, it is quite challenging. In previous work, when they construct the meta training task, they usually use random sampling from the graph, but it will ignore the tail node embedding, so the embedding of tail node are not unsatisfactory. So this paper, they want to learn a prior from the high node and adapt to the tail node. So in this work, the support site, they also sampled from the neighbors code subgraph of the query node. So this task is not a node classification or graph classification link prediction. No. So the task is to predict the embedding vector. So after training on a set of support nodes, we want to learn embedding vector for the tail node. I have introduced some methods about the graph level, node level, edge level enhancement on the few-shot learning on graph. So the adaptation in meta learning on graphs is also important because we want to learn a good a shared prior to the downstream task. But for the downstream task, we want to learn an adaptation for different kind of tasks. So there are also some works they focus on the adaptation enhancement, including different kind of enhancement and on different tasks. Here, I first introduce this graph-wise adaptation method named GFL. The basic idea is they want to recognize the topological variance across different graphs. So they want to learn a global pair for each individual graph and apply a get function to the global pair for each graph. So in each graph within each task, we learn this task specific adaptation from the global pair. Here, they extract a graph and use a prototype gene to learn the presentations. And it also use a hierarchical graph representation. It means for each graph, we can learn a different level of representation. And so for different level, in this kind of hierarchical graph representation can be adapted to different kind of graphs. So they use a Git aggregation for the prior knowledge to learn the specific presentation of each graph within different tasks. So this kind of work they called graph-wise adaptation. Here is another example for graph-wise adaptation. In this paper, they want to learn two knowledge. One is the general knowledge. It means this kind of knowledge is quite general to adapt to the downstream task. They also want to learn task specific transformation. Here, when we learn general knowledge such as use GN network to learn the prior knowledge of from the meta training task. When we want to learn task specific transformation, we in this paper they use feature-wise linear modulation to learn another parameter from the general knowledge. Here it has two parameters. One is the gamma is the scaling and beta is shifting. This is the parameter on the graph on the general knowledge. So from the general knowledge, we can learn different kind of scaling and shifting parameter for different tasks. And another one called meta TNE. This work they conduct the meta learning want to learn the embedding space. So they want to learn a task specific embedding. We can see that based on the structure module, we can learn the general embedding, right? This kind of embedding is task agnostic embeddings. So when do the adaptation, we want to learn a task specific embedding. It means we use transformation to learn different kind of embedding for each task. And this work is focused on the multi-level few shot classification. This work is also similar to with the previous works. Here they want to learn a task-specific feature matrix for adaptation. Here, they also use film we talked about before to learn the scaling and the shifting parameter for different downstream tasks. There are some other methods they use the adaptation-based enhancement. Here, this work they want to learn during the adaptation. They want to control the optimization standpoint for different tasks. Here, we can do that for different tasks. Maybe task 1 is very easy to learn, so it doesn't need more steps to do the training in the meta test task. And for the hard examples, they may need more steps. So this is interesting work. They want to control the optimization standpoint for different tasks, and they use reference reinforced learning based controller to learn the optimized step. Here, there are also work to use meta learning to deal with the dynamic graph modeling. In my background, I think there are quite not many work deal with the dynamic graph using the meta learning. So in this work, they first, let me introduce the dynamic graph. It means during the time going on, the graph may have no new nodes or new links. So it will change during time. So this kind of work, they want to adapt the general knowledge to from two aspects: the time aspect and the node wise. The time they want to learn different time interval may have different weight for our task. Here is a simple summary of the meta learning methods for few shot learning on graph. We can see that the existing research, they enhance the standard meta learning with structure or adaptation enhancement. But they have some drawbacks. First, they require abundant labels for the base class, as introduced by Prof. Fang. We need abundant labels for the base class. Even we have a few short labels for the query size in our meta testing task. Another one is they fail to leverage the vast amount of unlabeled data. We didn't see how they leverage the unlabeled data. So the unlabeled data, they can provide more data sample and more information to help us learn a more comprehensive prayer. The last one is the meta learning on graphs. They have a limitation about the IID augmentation in task distribution. So they can handle different types of downstream tasks. So here is a question. Can we address a diverse range of visual tasks on graphs without an extensive label-based dataset? Well, we can also better use the abandoned unlabeled graphs. In next session, we will introduce this kind of methods, pre-training strategy to use the unlabeled data and can adapt to various downstream tasks. So that's all. Anyone have some questions?
If you have any question, you can ask now, or if not, at the end of the tutorial, we can also answer more questions.
Yes.
Okay, so maybe we can start with the next part first. Then maybe for about 15 minutes, then we can have a coffee break. Then we can continue. So maybe Xintong, you can continue with the next part.
Okay.
Can you see the screen?
Yes, I can see the screen.
Okay.
Okay, thank you, Professor Fang. My name is Xintong Yu, and I'm glad to share some pre-training methods on graphs to you. And this part is pre-large language model, so that means these methods are basically focused on text-free graphs here. So as we know that label data are generally difficult or expensive to obtain in real-world scenarios. However, in contrast, unlabeled data are common and they are generally exist in different domains. And this unlabeled data, it could also be flexible applied to various types of downstream tasks here. So it's intuitive that we could use this large amount of the unlabeled data to train a pre-trained model to learn some prior knowledge. So this prior knowledge could be adapted to various downstream tasks to help us solve the future setting here. So that's why we developed some pre-training methods on graphs here. So basically, for pre-training methods on graphs, they generally first utilize a self-supervised method to learn some prior knowledge. These methods generally focus on learn some task irrelevant, intrinsic properties in the graphs, and so as shown in the figure B here. And then after we obtain the pre-trained knowledge, after we obtain the pre-trained model here, the pre-trained model it can serve as a prior knowledge, which could be further adapted to various downstream tasks here by an adaptation phase as shown in figure C here. So first, I like to introduce the pre-training strategies here. Basically, the pre-training strategies can be categorized into two parts. One is contrastive strategies and another is generative strategies here. So for contrastive learning methods, the functions by contrasting different instances at different scales. For example, given a target instance, an instance could be a node or a graph here. So given a target instance here, we first sample the positive instances and negative instances for this target instance here. And the goal of the contrasting method here is to bring the positive instances closer to the target instance within the latent space here. And in contrast, the aim of the contrasting method is to distancing the negative instances from the target instances here. And formally, the loss function of the contrasting methods can be formalized as this equation here. So for generative methods, they provide a different perspective in contrast to the contrastive learning methods. Different from contrastive learning methods, which aims to learn pure knowledge by discriminating different instances. Generative methods, they learn some pure knowledge by reconstructing different parts of a graph, such as node features, such as some local structures or global structures in a graph here. And some methods in generative learning strategies, they also combine both structural reconstruction and feature reconstruction here. And to be used either contrastive methods or generative methods, we can get a pre-trained model which entails some pure knowledge. So this pure knowledge can be transferred can be adapted to various downstream tasks to solve different downstream applications here. So one optimal selection for the downstream adaptation phase is fine-tuning methods. The fine-tuning methods work as follows here. So it first initialize a downstream model with the weights in the pre-trained model here, and it also equipped the downstream model with a task-specific projection head, so that we could train the task-specific projection head to tail to different specific downstream tasks here. So for fine-tuning methods, it's generally train all the parameters, all the parameters. That means both the parameters in the pre-trained model and the parameters in the task head here. So in this way, fine-tuning methods propose an optimal solution to adapt the pre-knowledge to different downstream tasks. So the fine-tuning methods is intuitive and reasonable, and also straightforward. However, it still has its limitations. So the first limitation of fine-tuning methods is that it needs the gap between the pre-training methods and the downstream tasks is different. For example, the pre-training task, in the pre-training task, we aims to learn some task irrelevant properties here, such as we aim to reconstruct node features. We aim to contrast different parts of the graphs here. But for the downstream task, it could be node classification, link prediction, which is totally different from the pre-training task here. So the gap between the pre-training tasks and downstream tasks could compromising the effectiveness of fine-tuning methods, which could lead to a suboptimal performance on different downstream tasks here. So this is one limitation of fine-tuning. And another limitation of fine-tuning is that fine-tuning methods, they generally needs to update all parameters, which means both the pre-trained model and also the task head here. So if the pre-trained model is a large model, it contains many parameters. So the fine-tuning phase could be quite inefficient. It could be costly to compute. And also, since in the real world, few-shot scenarios is quite common, which means we only have limited label data, it could easily lead to overfitting on specific tasks because the data is quite limited. So this is the two basic limitation of fine-tuning methods. To solve the limitation of fine-tuning methods, a very important technique, prompt learning, is proposed first in the NLP domain. Now, the large language models such as Llama, ChatGPT, DeepSeek, these methods all leverage the prompt tuning techniques. So the prompt tuning technique, it basically has two core ideas. First is that it proposes a unified task template, which is used to unify both it is used to unify the pre-training tasks and various downstream tasks. For example, in the NLP domain, the unified task template is a mask language model task here. It transfers all the downstream tasks, such as classification, such as generation tasks, to this kind of the mask language model task here. So with a unified task template, the gap between different task objectives could be unified. So the pure knowledge could be better transferred to the downstream task here. And another important technique in the prompt learning methods is the prompt engineering. In the NLP domain, prompt engineering basically is how we design some prompts. That means we artificially craft some prompts to guide the large language model to achieve some specific downstream task here. However, in the graph domain, it can be quite hard to solve this both two challenges here. That is, in the graph domain, we need to consider these two challenges as well. Is that the first one is how do we propose a unified task template or a unified graph template, because for graph tasks, there are different kinds of tasks, and also there are different kinds of graph types. So it will be quite challenging for us to design a unified template that can both unify tasks and can unify the graph types here. So that's the first challenge for the prompt tuning in graph domain here. And the second challenge is that how should we design prompts for graph methods? Because in contrast to the NLP domain, which is in NLP domain, we have some text which is easily for human to understand, and we can artificially design some prompts to guide the large language model to solve the task that we need. But for graphs, the graph structure is quite abstract. And given a graph, we can't easily understand what does the graph represent here. And we can't, if for text-free graphs, we can't design some artificial prompts here. So we need to, in contrast to human design, we need to learn some prompts for the graphs to solve different downstream tasks here. So next, I'd like to introduce some different prompt tuning methods in the graph domain here. But I think the time is quite close to the coffee break now. So maybe we could take a coffee break first. And after a coffee break, I will start to introduce you different kinds of prompt tuning methods on graphs. And I will also introduce you some graph foundation model, which is built based on the prompt tuning methods. Okay, thank you very much. See you later, guys.
So now I'll just goes to them. So let's go next one, handheld. Set prefig, yep. Sweet. Okay, let's see. Do you want to just I was gonna say, I'm just gonna try and figure out this. Yeah. I just wanted to get out of what's going to test. Yeah. Yeah, I just want to get someone to talk to me. That's the right session, right? Okay. Yeah, sure. Yeah, you can, that'll be.
You can use that.
Yeah, I'm still not seeing it. Is that the same meeting? So they're talking. Yeah, because theoretically we should be able to hear it through the speakers as well. See what it is. No, it's still wrong. So what happens is when there's audio there, that people line up to tell me that there's audio there, so I can check favor. Speaking, then I'll know. The other thing we can do, if you can jump in on the Zoom, maybe can you jump into the Zoom and speak from the Zoom into here? Yeah, sure. So you won't be able to speak. Okay. So we do need to have a presenter to test it. You can. Yeah, yeah. No, that's cool. Cool, that one, that's- So we did do the handheld on the speaker, last time. The next thing that we want to do is when our presenter will come back, so she can chat to us, see if I can test anything. So I made a couple of changes. So we're just waiting for her to come back. If that's all good, then my other plan works. If not, we can sort of do the same horrible plan. that we did last time. But it worked. It was fine.
I mean, yeah, as long as it is not.
It didn't disrupt anything.
Is this session chat? Yeah.
Yeah, unless there's somebody else that can talk into this in any form, which way.
I'm just asking, I'm just wondering if they have been involved with like. It's time to think about.
You were supposed to, you're saying there's another one in the next session, is that correct? And the same person. Even if nothing else, we probably want to do what we can to make sure that if any further remote stuff over the next few days goes well. Or at least I would like. Yeah, I'd much rather it be not a patchwork solution. Or not the patchwork solution, be the.
We recommend this laptop, this laptop is very swapped out.
That is a possibility, it might be a driver thing. The only thing that might be killing all of this is a language barrier, but I think we've gotten around that.
Yes.
Because we've got Realtek audio, which is the internal driver. So that's the internal driver for the laptop. Which theoretically mean that when I plug something into the headphone, you get and we did get a couple of things, so obviously it's the right side.
We have some USB-C,
No, I don't think that that's going to be the issue, and then it'll become another aggregate device as well, which will potentially complicate things. The other workaround is if we go to this back, because that's a double direction device, and that's an USB interface which you can take it both ways. We can try going from setting the output to that, output into the mixer. But the only thing will be is there probably will be a little bit of latency between what comes out of the computer and what's on the screen. Audio will be great, and that bypasses the whole concept of having to use a headphone jack entirely. It's just, so that's my next step. Yeah, there's certain features that we can tell, kind of, taking the shortcut and taking the little bit of cost cut, and I understand that version like it, but it does make things a little bit tedious at times. Like the main thing that I'm sorry about is they're running all Zooms off two computers on a Wi-Fi network rather than hardwired.
Yes.
And it's that, I mean, so far it's been okay, but
I think one reason, the rest of the reactor wires.
and it's always a big gamble. Something like the main. No, it is what it is. So we're just trying to manifest what we got.
It'll take break.
Yeah, so, we'll be able to get it sorted. Yeah, no,
That's like no.
We can potentially check it silently. I don't. I do have the method of doing that. Yeah, I do have a method of doing that.
But there's a guy, he makes it up, the guy who does right. That doesn't make any So it's a general idea. Look like sorry. The hold a small one. If it's solid, on the line, or user data, would be made by design in 550. What they mean is that we could get and then we could automatically right?
Because the mix that I've got sending to Zoom has still got microphone in it. So that's how I can talk silently to Zoom. But because there's only one mix that's doing the Zoom send and the record, that's where we get an issue. So you'll hear it as if somebody's listening back to the recording, they'll hear me speaking into the Zoom. That kind of makes sense. Yeah. So if the session finishes and then the recording stops, I can talk into Zoom silently without going through the speakers, and that won't do. So I'll have to do it outside of the session time. For that reason. Otherwise, it would be a matter of if it's just if it wasn't being recorded, I could just speak to the Zoom and only the Zoom would hear it. It's still recording. Oh, that's me.
The problem is it's all it's not in this direction I was thinking about the small expansions, you know, Japanese practice, use like them but I can feel it. I'm not going to theoretically because Netherlands Belgium implement the water public project. So they're going to promote it. And if you propose to them, so open this way. Or something with digital compliance, they will like public, new public. But yes, availability is definitely a problem. The problem on the project is that it's all public. But users can then directly see your data. This gives a bit more map. They can basically instead of taking back itself, they can do it through the soil. It's all- Basically, it's not related. But it's big. So it's,
好了，告诉我。现在人还蛮多的。
那可能你再稍微回顾一下，这边再
OK，
这个可能应该就不用讲，就是大概summary再讲什么。
OK。Okay. Okay, thank you for attending our tutorial. And I will continue with the prompt tuning part on graphs here. So let's first give a quick overview of the prompt tuning on graphs. So the basic two challenges for the prompt tuning on graphs here is the first one is how should we propose a unified template that could use to align not only the the pretext tasks and the downstream task here, but also we could propose some unified template that could bridge the gap between various types of graphs here. So that's the first challenge here. And the second challenge is that how should we design some task-specific prompt that could be used to guide the pre-trained model to transfer the prior knowledge to different types of downstream tasks to better solve this task here. So that's the two basic challenges in the graph prompt tuning part here. And different prompt tuning methods, they develop different strategies for solving these two challenges here. So in the following part, I will introduce different kinds of prompt tuning methods to introduce the graph prompt tuning methods. Okay. So graph prompt is one of the most representative prompt learning methods in this domain. It is ranked as the most influential paper in WW23 by Paper Digest here. And its motivation is what I have mentioned before, is that the first is how to design a unified task template, which could be used to unify pretext tasks and downstream tasks here. And the second challenge is how to design a task-specific prompt here. So in this work, we first propose to use subgraph as a unified instance to represent nodes level tasks, graph level tasks, and subgraph level tasks here. So because for a subgraph here, the biggest subgraph of a graph is the graph itself. So subgraph could represent a graph here, and the smallest subgraph in the graph is the node itself. So subgraph could be used to represent not only a node level task and graph level task, and also the subgraph level task here. So subgraph could be used as a unified instance. So with a unified instance here, another question is that what should be the unified tasks that we could use to unify different common tasks in the graph learning here. So the most popular tasks in graph learning, one is node classification, graph classification, and link prediction. All these three tasks could be unified under a unified task template. In this work, we propose to use subgraph similarity calculation as the unified task template. For example, for link prediction task, we could transfer the format of link prediction to compare the similarity between the connected nodes subgraph and the disconnected nodes subgraph here. Since under the homophily assumption here, connected nodes should have high similarity compared to the disconnected nodes here. And for node classification and graph classification task, we could transfer this classification task to compare the nodes or graphs, their subgraph similarity with the prototype of the different classes similarity. If the instance, if the node or the graph has the highest similarity with certain prototype in a class, that means these nodes or graphs should be classified into this class here. So in this work, the unified task template is the subgraph similarity calculation here. And with such a unified task template, we could better transfer the prior knowledge to different downstream tasks. But for different downstream tasks, they focus on different aspects. For example, for node level tasks, it may focus on the node itself more because node is more important here. And for graph level tasks, the global structure, it may contribute more. So for the downstream prompt tuning here, we need to design specific prompts so that we could better transfer the prior knowledge to various downstream tasks here. And in this work, we propose a quite simple but quite effective method. We use a single learnable vector as the classification prompt here, as the downstream prompt here, look at the prompt, it has the same dimension as the pre-trained embedding. So we use the prompt to modify the pre-trained embedding by element-wise multiplication here. It means we use the prompt to rewrite each dimension of the embedding here, because for different tasks, maybe a different dimension could serve as different importance here. So in this work, we use subgraph similarity calculation as the unified task template, and we design a learnable prompt for different downstream tasks to transfer the prior knowledge to each different downstream task here. So that's the key idea of this paper, and it's simple, but it's effective. However, it still has its limitation. So first of all, in this work, we simply use a straightforward pre-training task, which is link prediction, as shown in the figure B here. This raises question is that since there are many more advanced pre-training tasks here, so could they also be used to in this framework so that we could unify these more advanced pre-training tasks? So because they maybe could learn better prior knowledge compared to simple link prediction here. And another question is that in the graph prompt methods, the prompt is used to modify simply the node embedding here. However, for a pre-trained graph encoder, it generally contains multiple layers, and for each layer, it may contain different knowledge. For example, for different layers, it may contain a different level of structure knowledge here. For example, the first layer may only contain the one-hop neighborhood knowledge, and the second layer output embedding could contain two-hop neighborhood knowledge here. And for more layers, more knowledge could be contained. And each layer, the output of each layer is different, and they contain different knowledge. So could we design a layer-wise specific prompting method so that we could use the hierarchical knowledge to learn better, to better transfer the prior knowledge to the downstream task here? So these two motivation leads us to propose another work, the generalized graph prompt here. So in this work, we first prove that all contrastive learning methods can be unified as subgraph similarity calculation here. Since all contrastive learning methods, they can be unified under this format. And this format is a kind of a subgraph similarity calculation format here. So all the contrastive learning methods could be unified, could be applied in this framework. So let's solve the first challenge here. And for the next challenge, in this work, we design a layer-wise prompt tuning methods. Specifically, we also design a learnable vector as the prompt. However, for each layer, we design a specific prompt to modify the specific embedding of features of different layers. For example, we first use one prompt vector to modify the features here, to modify the node feature. And for this line, we use another prompt to modify the output embedding of the first layer. And in this format, we use another prompt to modify the final embedding. So we use all these these prompted embeddings to get a hierarchical knowledge here, and this hierarchical knowledge will contain the overall knowledge in the pre-trained graph encoder here. So this could achieve a better performance compared to simply use one prompt to modify the final embedding of the pre-trained graph encoder. So that's a better way to do the prompt tuning here in this work. So these two work propose different methods for tuning on homogeneous graph. However, many real-world graphs, the nodes and edges has different types which constructs heterogeneous graphs here. So the heterogeneous graph is more complex than a simple homogeneous graph since it has more node types, more edge types. And so this raises another question is that how should we, could we design another unified template which could be used to unify not only the task, the pre-training task and the downstream task, but also we could use it to unify homogeneous graphs and heterogeneous graphs. So that we could, so because with such a unified template, we could use some homogeneous graph pre-training methods to pre-train a graph encoder, and we could learn, we could transfer the homogeneous pre-knowledge to solve heterogeneous tasks. So that's quite challenging, but that's also very important. And if we have designed such a unified template which could be used to unify graph types and also the tasks here, so how should we design some task-specific prompt so that we could tell to different kinds of downstream heterogeneous graph, heterogeneous task here. So that's the, by these two motivations, we design another work called HG prompt heterogeneous graph prompt here. So in this work, we first design a unified graph template. For a unified graph template, we assemble a heterogeneous graph to several homogeneous graph. For each homogeneous graph, it only contains one type of nodes or edges. And also, we also assemble another graph with only the topology of the origin of heterogeneous graph without considering the nodes types or edges. So these sample graphs could serve as a graph template since each sample graph only contains one type of nodes. So it could be considered as a homogeneous graph here. So for each sample graph, we could directly leverage the homogeneous graph prompt tuning methods to tuning them. So to unify the pre-training tasks and downstream tasks here, we simply follow previous work, follow graph prompt and generalized graph prompt. We use subgraph similarity calculation to unify different kinds of the pretext tasks and downstream tasks here. And with these two template, graph template and task template, we could unify homogeneous graph and heterogeneous graph, and also the pretext tasks and heterogeneous downstream tasks here. So, so now we could use the template to better transfer the prior knowledge. And the next question is that how should we transfer the heterogeneity specific knowledge to different downstream tasks here? Because for different downstream tasks, we may focus on different kinds of heterogeneity. Therefore, in the downstream task here, first we use a simple Fisher prompt, which is same as the previous work, which is used to modify the embedding of different sampled graph here, since each sample graph is a simple homogeneous graph. And then we design a heterogeneity prompt. This prompt is used to weight the importance of different sampled homogeneous graphs here. So we use by the guiding of the heterogeneity prompt here, we fuse the embedding of these sampled homogeneous graphs to get the final embedding. The final embedding could serve as the raw embedding of the heterogeneity graph here. So by using these two prompts here, we could transfer the prior knowledge to different type of the heterogeneity downstream tasks here. So, however, most of all these previous work, all these previous prompt tuning works, they rely on one assumption, that is homophily assumption, which means they think that if two nodes are connected, they have higher similarity compared to disconnected nodes. However, in real-world graph, not all graphs are homophily, but there also exist some heterophily graphs, which means, for example, for a homophily graph, a homophily edges means the connecting nodes, they share the same labels. However, in contrast, for a heterophily graph, in a heterophily edge represents that the connecting nodes, they have different type of labels here. So, for heterophily edges, the homophily assumption is not work, and therefore, the previous that is something that the previous prompt tuning work that they never considered about. So for these methods, they could lead to suboptimal performance on the heterophily edges. And moreover, for real-world graphs, these graphs are generally not simply homophily or heterophily, but they are non-homophily, which means some edges in your graph is homophily, and some graph in the edges, some edges in the graph is homophily, and some edges in the graph is heterophily. So in real-world graph, there are a mixture of both homophily edges and heterophily edges. And moreover, even for a single graph, this homophily ratio could change across to the downstream node classification, the node level here, that's shown in this figure B here. For example, in this graph, if we use the gender to classify different nodes, so this is a heterophily. It has low homophily ratio because the connecting nodes prefer to be different gender, because male may prefer connect to female, and that's why in such graph, if we use gender to classify the nodes, it's low homophily. But if we use topic to classify these nodes, then it's a high homophily graph, because the connecting nodes, they are preferred to have a similar hobbies. That's why they could connect with each other. So the homophily ratio of a single graph could change according to the downstream task here. And moreover, as shown in the figure C here, even for different nodes in a single graph, different nodes, they have different homophily ratio here. For example, in this graph, in this figure here, on core data site, most nodes has high homophily ratio between 0.8 to 1, but there are also some low homophily ratio nodes here. So that means for different nodes, we should design node-specific prompt tuning methods to capture their characteristics. So motivated by these parts, in this work, we design another prompt tuning method called ProNoG here. So we first gave a theoretical insight that we prove that not all contrastive pre-training methods could be used to solve the non-homophilic graph learning task, because some pre-training methods, they rely on the homophily assumption. So any of those tasks without the dependence on the homophily assumption here, they could be applied to solve the non-homophilic graph learning task here. And specifically for the prompt tuning part, in these methods, we design a node-specific prompt tuning methods, which could capture each node's node-specific characteristic here. So how do we achieve that? So in this work, for each of the, in contrast to design a single graph prompt as we do in previous work, in this work, we tune a condition net. This condition net is a hypernetwork. It's based on some condition to generate a prompt matrix. The prompt matrix means each row of the prompt matrix serves as a prompt for a specific node. So by this prompt matrix, we could modify each node in node-specific pattern. So in this work, the condition we use to generate the prompt is that the local structure of each node, because we consider the node homophily ratio is considered by its local structure here. For example, as shown in figure C here, since if two nodes are connected, we think this edge is homophily edge, and if they are disconnected, we think that is a heterophily edges. So we could use the one hop subgraph, or we could also use more hop subgraph to represent its local characteristics. So we read out the local subgraph of each node to obtain its characteristics, which is served as a condition used to input into the condition net to generate a prompt for this node. So in this way, we could generate different prompts for different nodes based on their specific characteristics here. So by these methods, we could obtain a better performance compared to pure prompt tuning methods, and we could also solve the non-homophilic graph learning task here. And moreover, in real-world graphs, in real-world scenario, there are many graphs, their structures may evolve by time because for example, the graph structure could change and the node features could change as well. And for such dynamic graphs, there are still rarely some prompt tuning work to solve this problem on the dynamic graphs here. So in this work, we aim to propose a dynamic prompt learning methods here. And there are two motivations in this work here. So the first is that we know that in a dynamic graph, we first need to use some pre-training methods to pre-train to learn some prior knowledge. However, the prior data could have a temporal gap and with the downstream data. For example, we may use some data before 2020, and we may use the data after 2020 to train our downstream task here. So the temporal gap, the temporal variation could lead to suboptimal performance here. So that's first challenge we need to solve. And also we also have the gap in the task objective here. And moreover, a more challenging task in dynamic graph is that there are also some involving patterns between both nodes and time points. For example, as shown in the figure A here, a professor may check a paper, may read a paper during the noon here, but for the same guy, for the same professor, when he come back home at night, he may deal with some family issue here. So for a single node, its behavior may change according to the time. And moreover, for different nodes at the same time point, we may exhibit different behavior here. For example, at the noon, a professor may read a paper, but a student, a CS student may coding here. So for even at the same time, different nodes could behave differently. So there is an involving patterns between the nodes and time points. So we need to design a specific methods to capture both the node pattern and the time pattern between each other here. So in this work, we first propose a dual prompt. The dual prompt is quite simple. It is similar to previous work that we use the node prompt and the time prompt, which are two learnable vectors here, to modify the node embedding, to modify the node features or node embeddings here. And we use the time prompt to modify the time feature here, so that we could unify, we could better align the downstream node encoding and the time encoding with the pure knowledge here. And moreover, to capture the emerging patterns between the nodes and time, we design a dual condition prompt methods here. Specifically, since as we mentioned in the motivation part, a node's behavior may change according to time. That means time could be used as a condition to modify the node's features. So that's why we design a time condition net here. It is conditioned on time, and the input is the time feature. So we use the time feature to generate some time condition node prompts to tune the node's embedding here. So in this way, we could capture the time impact on the node's features here. And in contrast, even at the same time, different nodes may behave differently. So for the node, so we design a node condition net, which input is the node's embedding, and it generates node condition time prompt to modify the time features here. So in this way, we could capture the mutual influence between the nodes and time here, and the modified features, the modified node features and time features is then used in the pre-trained dynamic graph encoder to solve different downstream tasks here. So in this way, we could easily solve the dynamic graph learning method, the dynamic graph learning task here. And besides this work, all this work, the previous prompt learning work, they simply leverage one single pre-training tasks to learn pure knowledge and transfer to the downstream tasks to solve different types of downstream tasks. So could we also leverage diverse pretext tasks to learn a more comprehensive pre-training knowledge? Because different pretext tasks really focus on different parts of the graph properties. For example, for a feature reconstruction task, it may focus on the feature itself more. And for a graph reconstruction, it may focus on the graph global structure here. So if we could combine different kinds of pretext tasks, we could learn a more comprehensive knowledge here. However, it's not easy to do that because of course, there are some straightforward way we could directly combine different kinds of pretext tasks. But this could, because the objective of different pretext tasks is different. So such the gap in different pre-training tasks could lead to a conflict in the pre-training process, which could result in a worse performance in contrast to any improvement. So we need to design a specific pre-training methods to align these pre-training tasks so that they could work in a cooperative way here. And as we have already developed pre-training methods that could combine different types of the pre-training tasks, then how should we transfer both the task-specific knowledge, because each pretext task, they could contain some specific knowledge, and all these pretext tasks could contain a global pure knowledge. So how should we transfer both the specific knowledge and the global knowledge to the downstream task here? So these are two motivations of our work here. So in this work, we propose a method called multi-G prompt here. And in this work, first, to unify different kinds of the pre-training task here, we simply design a pretext token here. A pretext token is simply a learnable vector, which is used to modify the features of our query, of our pre-training data here. However, for different pre-training tasks, we use a specific pretext token to modify the features. And the modified features is then used to pre-train the pretext task here to get a pre-training loss. And we're combining all pre-training loss as the final pre-training loss to learn to train the overall pre-training model here. So in this way, all the pretext token is quite simple and easy, but you could effectively unify all these pretext tasks here. So this pretext tasks could work in a collaborative way rather than conflict with each other. And after we obtain the pre-trained graph encoder here, we need to transfer the pure knowledge to different downstream tasks here. So each pretext task, it contains a specific knowledge. And for different downstream tasks, maybe some downstream tasks may rely more, may rely some knowledge closer to certain pretext tasks. So we need to rate the importance of different pre-knowledge from different pretext tasks here. So here we design a composed prompt to rate the knowledge of the different pretext tasks here. The composed prompt is a learnable combination of the pretext tokens here. Because in the pre-training task, in the pre-training phase, we use the pretext tokens to unify different pretext tasks, and each specific pretext token, it could contain some pre-knowledge from different pretext tasks here. So we simply need to combine these pretext tokens so that we could get the composed prompt, which could be used to rate the importance of different pretext tasks here. And then the composed prompt is used to modify the downstream node embeddings or node features here. And also, we also design an open prompt here. The open prompt, it serves as to transfer the global knowledge to the downstream tasks. It's simply a learnable vector here, same as the previous works, and same as the graph prompt here, because all pretext tasks, they could be considered as a huge pretext task here. So it contains some global knowledge which could be transferred to downstream tasks by the open prompts here. So in this way, by the multi-chip prompt, we could learn more comprehensive pre-knowledge, and we could transfer both the task-specific knowledge to downstream tasks and the global knowledge to the downstream task here. So in this work, we aim to leverage diverse pretext tasks. However, in the graph learning domain, there are different kinds of graph data. For example, social networks, commerce network, molecules, proteins. There are different kinds of graph data. So these graph data, they construct a huge knowledge repo. So can we align all these? Can we leverage different kinds of graph data to train a graph foundation model? Same as what they do in the NLP domain. They use huge data to train a foundation model so that they could better solve different kinds of downstream tasks here. No matter the downstream task is focused on the, for example, on the scientific article domain or the molecular domain. So we designed two different works to solve this challenge here. That means we design some graph foundation model here. So okay, so let's continue with the tutorial here. So however, it's quite difficult for graph domain to align different domain graphs here, because in contrast to text data, for text data, we could easily use a text model to transfer all text into the same latent embedding space. But for graph data, a different domain graph data, they have the feature is not aligned. For example, the dimension of different graph data is different, and also the meaning of different features is different. For example, for a scientific graph, for a scientific article graph, a feature, each dimension in your feature could represent, for example, such as whether a word, a specific word, exists in this graph. And for however, for a molecule graph, the feature may represent some properties of the atom here. So it's quite hard to align these different domain graphs in the feature space here. So that's the first challenge. And also, different domain graphs, they have different structures here. So how should we align the feature of to align the gap of different in the feature of different graph domain, and also the structure gap of different graph domain here? That's two major challenge in the developing a graph foundation model here. So for this tool, for the MDGPT, we develop a method to align the feature gap. And for SAM-GPT, we design a method to align the structure gap here. So in the MDGPT, we inspired by our previous work, multi-G prompt here, we design a domain token for each domain here. So we first use a dimensional alignment methods to align the dimension of different graph domain here. The dimensional alignment method could be a simple SVD here, which is used to decline the dimension of different source domain here. But however, even with the feature dimension aligned methods, the feature is still not aligned in their semantic meaning here. So we need to design another methods to align their meaning here. So we use domain tokens here. For each domain, we pre-train a specific domain token, and the domain token is used to modify the features of different domains here. And in this way, different domains could incorporate with each other. And then we concatenate all the pre-training data from different domains and use to pre-train a graph foundation model here. That is the graph encoder here. So for the downstream adaptation, the downstream task would be on a different domain, which is unseen in the pre-training part. So we also need to adapt the pre-training knowledge from different source domain to a new target domain here. So we use two prompts here. One is a mixing prompt, which is a combination of the domain tokens, since each domain tokens may contain some prior knowledge from each different domain. And some domain may be more closer, more helpful for this target domain, and some source domain may be less important for this target domain here. So the mixing prompt, it could rate the importance of different source domain here. And also, all domains, they construct all knowledge here. So we design a unifying prompt here, which is a learnable vector, which could be used to transfer the overall domain knowledge to the downstream task here. So the idea of MDGPT is quite simple, but it's also effective. And the idea of SAM-GPT, which is used to align the structural gap, is similar to MDGPT, but it focuses on the structure aspect here. Since for the graphs here, we consider that rather than nodes, edges, they better represent the graph topological. So in contrast, to modify the nodes, to modify the nodes features, we should modify the edges to align them in the structure, to align them the structure gap here. So in this work, we also develop some structured domains for different domains. We also develop some structured tokens for different domains. However, the structured token, they are used to modify the edges here. And for each layer of the graph encoder, since different layer of the graph encoder, they may contain hierarchical structural knowledge. So we develop different tokens for different layers here, so that in the message passing process of the graph encoder, the structure tokens could guide the structure-based message passing process here. And in this way, we could align the structure gap between different domains here. And also, in this work, we need to align the feature as well. So we simply use MDGPT as the feature alignment methods. And for the downstream adaptation, since the downstream domain could be different in the structure from the source domains here, we also need to adapt the pure knowledge from different structure of the pure structural knowledge from different domain to the downstream domain here. And we also design a specific prompt which is used to which is a combination of the domain tokens of the pre-trained structure tokens from each domain, and a holistic prompt which serves as to modify the overall structural knowledge to transfer to the downstream task here. So in this way, the MDGPT and the SAM-GPT, they are similar in the technique, but they focus on different types and they focus on different challenges here. One is to solve the feature gap in different domain, and another is to solve the structure gap in different domain. But we could use some similar techniques to solve these methods and develop a graph foundation model here. And that's shown in this table and in this figure here. We can see that for most baselines, when we add more source domains for pre-training, the performance would generally decline because these methods lacks effective domain alignment methods. So adding more domain would generally lead to worse performance rather than improvement. In contrast, MDGPT and SAM-GPT, they could perform better when more source domains are introduced because we use some effective domain alignment methods here. So overall, the previous work that we have mentioned, they generally focus on text-free graphs. However, for many graphs, there are lots of textual data which could be used to learn a more comprehensive. So, and moreover, in these days, LLMs, large language models, they have achieved significant performance. So this raises question is that, can we leverage large language models to use the textual data in these graphs, thereby so that we could improve the performance of the graph feature learning here. So in the following class, we will introduce the LLM-based methods on graph learning here.
Hi, can you see my screen?
Yes.
Okay. Okay, can I start now?
Yes, yeah, please.
Okay, in this section, I will introduce pre-training approaches, integrate graph, and large language model. I will introduce the pre-training approaches, including the contrastive pre-training and large language model. And for the adaptation, I will introduce the prop tuning and parameter efficient fine-tuning methods. First, let me introduce the contrastive pre-training, integrate graph and language model. Here is a model focused on molecular pre-training. Here we can see that there is a molecule encoder and a test encoder. So the task is to pre-train a contrastive relationship between each molecule and the text description. So here we have a graph encoder and text encoder, and it also add a projector layer to align the space of graph and language. So we have a projector to learn the relationship between the molecule and the positive, negative text information for the molecule. Here is another contrastive pre-training methods named G2P2. It focuses on the node classification. In this graph, each node has textual description. So the goal is to align the text information and the graph structure information. So we have two parts. First is the graph encoder, and the bottom is text encoder for the text information of each paper. And the loss function design is quite interesting. We have three contrastive loss. The first one is the text and the note embedding. Another one is the text summary. It is a summary in representation of the text and its neighbor nodes. So here is a lot about text summary and text embedding. And the last one is text summary representation and the node structure embedding. So we can learn the alignment between the text and the graph structure. This work, Python, it uses language model pre-training methods to pre-train the model. It used two pre-training strategy. Mask language model to predict the masked token. And another is mask node prediction. We can mask some nodes and predict the node feature. So this kind of pre-training, it follows the pre-training in language model in NLP domain. There are also pre-training methods combine the graph and the language model. Here, this work they use LLM to encode the node embedding and use a graph encoder to learn the graph structure information. And during the training, in this work, they use link prediction task to pre-train both the RM and graph encoder. There are also other works they use the language model pre-training. Here, this work instructs GLM. They use natural language to describe the graph structure. We can see that we can use the text to describe the one half of multi-half neighbors and the structure, and we can do multitask. It depends on what kind of prompt and what kind of task you want to pre-train during the pre-training stage. we can design, we can use this pattern to do multitask learning. For example, we can do the node classification and link prediction. This multitask learning can be integrated into one single pipeline. And the pre-training is the same with the language model to predict the next token. Here is a pre-training work. They integrate LLM and GN. This work they can conduct on multi-domain graphs. For example, the citation network, molecule graph, and knowledge graph. Since each node in the graph they have text information, so we can describe them in a same prompt and feed them into LM to get the embedding. And following that, they also construct a feature graph with prompt, and the prompt can be designed based on the task you want to predict. And the final layer is a single GN layer to learn the downstream task prediction task. For the adaptation, we divided the existing work into prompt tuning and parameter efficient fine tuning. This kind of work they ever use learnable prompt and conduct on various tasks, node level, edge level, and graph level. First, this is G2P2. After pre-training, before like I have introduced this work use contrastive learning pre-training with 3 laws. Remember that. So after pre-training, how can we do the prompt tuning about the downstream task? They provide 2 kind of prompt tuning. First one is the discrete prompt tuning for live-shot learning. Here we have a pre-trained GNN, and we have the target node embedding. So the discrete prompt tuning, we use discrete prompt. It means it is a sentence to describe the task. For example, here the task is the category of the paper is Y. So here for the after we pre-training, we can compute the similarity between the node embedding and the text embeddings to predict the label of the node. For few-shot learning, we have some label data for each classes, few-shot label data. So here we learn trainable prompt embedding for each label. So this is also compute the similarity between the target node and the text. So the parameter of the prompt can be trained based on our labeled few-shot samples. For this paper, one for all, they propose prompt tuning methods. Here we can see that there is a node of interest. It means we want to predict the label of this node, or the link of these 2 nodes, or the graphs. It also have an NOI graph. It is the graph constructed from the node of interest and its neighbor nodes. And for prompt tuning, we add NOI prompt node. Here for usual scenario, the NOI prompt node is a prompt template for describe the task. For example, this is a prompt node. So the task is the graph classification on molecule properties. So we can use a language model to learn the embedding of the node prompt. Here the node prompt is also linked to the class node in this graph. And for here is the class node information. It is also described by language. We can see that here is an example. Prompt node, molecular property. The molecule is affected in such. So we can learn. We can add the new text information to the graph and do the downstream task prediction. And for the future scenario, remember that we have a query, we have an NOI graph. So for the query NOI graph, it can be linked to other NOI graph in the support site. So we can train based on this graph, this integrated graph to also for the downstream task. And note that this paper, they can conduct node level, link level, and graph level task. And it can also integrate multi-domain data because we use a common prompt template to represent the node and the task. Here is a parameter efficient fine-tuning work. This work have two pre-trained stages. It focuses on the molecular caption. It means we have a molecule and have text information about this molecule. So the pre-training stage 1 is to if you are familiar with the belief tool, you can easily understand this pipeline. So generally speaking, it want to match the graph for the molecule and the text information of the text description of the molecule. So it has contrasting and matching and the molecular caption subtasks to pre-train the model. And during the stage 2, they want to generate the description of the molecule. So it uses a language model to generate the text. But here there is a cross-model projector to align the hidden space of the graph and the text. So during fine-tuning, they will freeze the graph and the language model to prompt just fine-tuning the graph encoder and cross-model projector. And here they use parameter efficient fine-tuning. They use LoRa to efficient adapt the prior knowledge to downstream task. Here is another work use PEFT. ChatGPT, they first pre-train the graph and text matching network. Actually, they use the G2P2 module to first pre-train a text-grounded structure encoder. So the latent space has already been aligned in some way. So during the following pre-training, they add an alignment projector to learn to map the knowledge of task and the text information and the graph information. So during all the pre-training and fine-tuning stage, they only fine-tune the projector, and they design different kind of tasks using the LLM language, and to predict the text token for note classification and link prediction. In the third part, they use a CUT prompt and task distillation to make the inference to quick adapt to the downstream task. So the general idea of this work is they want to align the graph domain to the large language model and to inject the information of large language model to help better improve the graph learning task. Another PFT work is graph translator. In previous work, the combination of GN and LM, they have different kind of ways. For example, here LM can be an enhancer to get the node feature from the text information of the node, so it can enhance the semantic representation of the node. And LM can also be a predictor, such as the ChatGPT. In ChatGPT, in the prediction part, we use language model, we use text information to ask the large language model to predict the next token. Here, they need to predefine the task. We know that we should define the prompt type and the task. So this work they want to they want to use an open-ended task. It means we can define the task by these instructions and infuse this instruction to the large language model. Here is the detail of this model. First, they have a frozen graph model, and for the language part, they use some producer to do some semantic understanding, including the summary of some node information, summary of neighbor information, and summary of their communities. You can also design other kind of tasks to better understand the text information and the relation of different nodes. Then they apply it is also like the belief tool to align the graph structure in embedding and the description tokens. Here in the pre-training they use two laws. The first one is the graph model and text alignment. In stage two, they align the graph model and large language model. here the large language model is also frozen. So the whole pipeline, the only fine-tuned part is here, is here, translator parameter. So it is also a parameter efficient fine-tuning. Here is a brief summary. We can see that the pre-training approaches they can employ in self-supervised pre-text tasks on the unlabeled data. And the pre-training approaches, I think they are more effective in the scenario. The labeled data are limited. And without a pre-existing set of annotated tasks. So when we have a large amount of annotated label data, I think maybe meta learning can perform better because it can leverage in the meta learning task and better adapt to the downstream task. And for the pre-training methods, the parameter efficient adaptation strategy can be a promising direction for future learning on graph. In the following part, I will introduce several hybrid approaches. Hybrid approaches means we integrate the pre-training and meta-learning strategies. We can first adopt a pre-text task to pre-train a graph encoder. So we can, during pre-training, we can use unlabeled data. Then we can adapt the pre-trained graph encoder to downstream tasks and use meta-learning. Here is an example, combine the pre-training and meta-learning methods. This paper, they want to follow the pattern of large language model for training. We can see that in NLP domain, we have an input sentence and the prompt sentence. And we want to directly predict the next token. So how to do like this in graph domain? In graph domain, we have the input graph. It is like the input sentence in NLP domain. So how can we design a prompt graph? Just like the prompt sentence in NLP domain, and like the model to predict the answer of the input and the prompt graph. So this work, this is the motivation of this work. So to better integrate different kind of different level tasks of graph tasks for the node edge and graph level, they unify the node level and the edge level task into a graph level task. Because for the node level, the input is one node, but we can also integrate the neighbors of the node, so it can be seen a graph. And for the edge, we can also get the one-hop or two-hop neighbors to obtain the graph tab. So it unified the multi-level graph task into graph level. So the next part is they want to design a prompt graph. Here they add some we can see take them as some virtual link or virtual node to get the prompt graph and integrate it with the original graph to learn to learn the graph encoder for the graph level task. And the whole pipeline, they apply meta learning to learn the prompt parameter. Here is a network. They first pre-train a graph transformer. Here, after this, they inject a virtual node. Here, we can see that it is a parameter, a prompt parameter. We want to learn during the training stage. So it is quite similar with the previous work. They want to add some new virtual node to better learn the relationship within the nodes. And during this pipeline, they also use meta learning to learn the prompt parameter. Here is another work. This work they we have a pre-trained gene. So this work they want to address the problem of the set the pre-trained gene as a black box setting. It means we we can't get the the parameter or the structure of the gene. And we can only obtain the output of the gene model. So they want to do is how to extract the useful information from the gene model and adapt to new tasks in a downstream task. So they apply the meta learning framework to help us better adapt the prior knowledge into downstream task. And in this model, they they extract the useful information based on the output of the pre-trained gene. They use an information bottleneck in strategy to learn the mutual information about our input, output, and the label. After that, we because maybe we have some large graph, so we can reduce some unuseful information and extract the subnetwork with useful information about this task. So they have an subnetwork in extraction stage. It is also a combine of pre-trained model and meta learning. So that's all. In the following part, Prof. Fang will introduce the future research avenue of future learning on graph.
Right. Thank you, Yixia. Let me share my screen. Okay, so in the I think remaining 15 minutes, we are going to discuss about what are the possible future directions. Okay, so one direction is in about different kind of problems we can explore. So in the previous in the work we have introduced for structure scarcity learning on graphs. So most of the existing approaches is actually using a meta learning approach. That means you need to have a set of base classes, right? And the base classes has to be labeled. Then we learn a prior and transfer to the novel classes, right? So in a way, we leverage the structure rich part of the graph and try to help the structure scarce part. But for meta learning approaches, there is a constraint is that there's assumption that the meta training tasks and the meta testing tasks are identically and independently and identically distributed, right? So if there are certain difference, for example, the distribution are not identical in the base tasks and the novel tasks, which is common because there could be distribution shift when dealing with different tasks. So in this case, meta learning approach that assumes IID distribution may not work well, right? So instead, we need to think about how we can perform some pre-training on the base tasks and then try to adapt to novel tasks that may have a different distribution from the base tasks. So we have to design methods to bridge the gap between base and novel tasks. All right. Then another problem is how can we deal with large scale graphs for few shot learning, right? So in many existing methods, the few shot learning is probably performed on a smaller scale graph, but many large scale graph benchmarks, we can have, for example, over like 1 million nodes or even more. Like in some data sets, there's 100 million nodes, right? And the edges can be more than 1 billion edges. In such a large scale graph, existing method may overlook the connections between this among distant nodes on the large graph. So different parts of the graph may have we may need to have fine-grained adaptation strategies to deal with such distant localities on a very large graph. So of course, apart from dealing with these distant localities on a large graph, efficiency and scalability is also a concern. Can we enable a very efficient inference, few shot inference on large graphs? And there are also a lot of complex graphs, right? So the typical graph we deal with are just nodes and edges, right? So we also have a heterogeneous graph where we can have different type of nodes. For example, in a paper citation network, we can have papers as nodes, authors as nodes as well, right? In a recommendation system, we can have users as nodes or items as nodes, right? But apart from these kind of graphs, which are still based on nodes and different kind of nodes and edges, we also have a 3D graphs. So 3D graphs are very common in biology and chemical applications, right? So the molecule structures have 3D information. So the molecule structures, they not only have the two-dimensional topology, for example, the different bonds between different atoms, but they also have a three-dimensional position information, right? So this three-dimensional position information is not captured in two-dimensional topology structures. How do we effectively leverage this three-dimensional positional information is an important question. And then for multimodal graph, right? So we have actually seen some of the multimodal graph with text information. So in many cases, the graphs, the nodes have textual descriptions. For example, in a e-commerce graph or in a social network, users have profile information. This profile information can be a textual description of the user, right? Then items in a e-commerce system, they also have product descriptions or user reviews. Apart from this textual information, we may also have visual information, right? On social media, there are a lot of videos and images, And in knowledge graphs, the same entity can have a visual representation as well, right? So if you go to Wikipedia, many of the Wikipedia entries, they have an image for the corresponding entity. So how do we leverage the multidimensionality? We need to a lot of research questions here. For example, how do we align different dimensionalities or align different modalities, right? The text modality and the image modality and the graph structure, they should be consistent with each other rather than contradicting each other. And finally, we may have complex dynamic systems, right? The nodes and edges, the features of the nodes, features of the edges could change rapidly, right? In social networks, in urban systems, dynamic graphs is a very common representation. How do we deal with the dynamic nature of the graph? It is going to be another important future direction, right? And the next is cross-domain training. So like in natural language processing, when we train a language model, all right, or in computer vision, when we train a foundational model, we typically combine data sources from different domains, whether this is a news article about a sports news, or it's a Wikipedia article on science and mathematics, or it's a medical paper. All these different domains of text data can be combined to train a single foundation model. But in graph, there is this challenge of significant differences between different domains. So we actually have introduced some of these challenges earlier in our one of the earlier part, right? So we say there is certain differences in the feature distribution and differences in the structure distributions, right? But our previous work focused more on the text, so-called text-free graph. So these graphs, they do not have textual information. But going forward, there is also, we want to leverage there's a lot of text attributed multi-domain graph, right? How do we leverage the text information to deal with and integrate the graphs from different domains, so we can train a foundation model that incorporate not only text attributed graphs, but also text-free graphs. And of course, another very important direction is interpretability, right? So current models, whether it's graph neural networks or graph transformers, they mostly operate in a black box setting, all right? So how to explain the model weights, right? How to explain or interpret the predictions is an important direction, especially in certain critical applications. For example, in biomedical domain, right? When you are trying to develop new drugs, right? Or in financial domain, when you are trying to detect outliers and anomalies on a financial network, right? Typically, a black box output is not easily to be accepted, right? You need to come up with some explanations why this is actually an anomaly. For example, this is a scam case, or it's there's a money laundering case, right? So in these critical settings, interpretability is an important research direction. And finally, on graph foundation models, right? So graph foundation model, earlier we mentioned that one criteria is that we need to build it upon multiple data sources. We can't just train on one graph data, even if the graph is like with 1 billion nodes, it's still just a single domain. We need to combine data from different domains. However, another aspect of graph foundation model is that we need to enable different downstream tasks, right? The task should be, we should be able to learn a foundation model, that the foundation model can be used to address a wide range of downstream tasks. So we call this homogenization, right? Whether it's a node level tasks, edge level tasks, or graph level tasks, right? So we should be able to utilize the same foundation model to address these different tasks, right? Much similar to a language foundation model. When you train, after you train a language foundation model, it can be used to solve different tasks, like whether it's sentiment classification or whether it's question answering, all of them can be solved using the same model. So homogenization of the tasks is also an important aspect of graph foundation model. Right, I think that comes to an end of this tutorial. So I just put up these links again. So this is based on the surveys, and we also have a corresponding GitHub resources, right? Including the slides of this tutorial is also available in the first GitHub repository here, right? So I think we have a couple of minutes. If there's any question, you are welcome to ask here. So any questions? Yes, please. Yeah, they have a mic.
Thank you for the tutorial. It was very interesting. I have more than a question, maybe a commentary that is based on the possibilities of foundation models on graphs, because in foundation models on text are based on tokens that are part of the language. But if we think about graphs, the problem is that the nodes and the links in different graphs represent different concepts or different elements.
Yeah.
So do you think that it is possible to create a foundation models and graphs thinking that a graph is mainly a representation and not a base phenomena that's the language natural, because it's more a representation that is related to an abstraction of different data sets.
Yeah.
And if we see foundation models in text, are based on a natural expression of the language.
Yeah, thank you. So I think that's a very good question. So in fact, that's the challenge of building a graph foundation model. So we know in graph domains, different graphs they could have totally different characteristics. Like if you are looking at a citation graph, they have papers as nodes. But if you are looking at a social network, they have users as nodes. Or if you have a biological network, the nodes could be drugs, proteins, or atoms, right? So I think there are two ways to answer this question. One is perhaps we do not need to build a foundation model that for all the domains, but for similar domains. For example, we can have a graph foundation model for biomedical or chemical domains. Then we can consider different kind of graphs there. So for example, molecular graphs, okay, protein structure graphs, drug interaction graphs. So although they are different graphs, but they have similar domain. There are certain semantics that's common between them. So I think that's still possible if they are related domains, right? So the other approach is we also need to address the differences between these data sets. So even if it's all biomedical domains, there are still differences between different data sets. The drug interaction graph and the molecular graph and or protein interaction graph, they are still different. Each node represents different things. It could be drugs or proteins or molecules or atoms, right? So we still need to design some way to bridge the gap. So in fact, some of our previous work is actually trying to explore this. We try to design certain learning certain special tokens from each domain and try to integrate these tokens so that they try to cooperate with each other rather than conflict with each other. So, but the progress is still limited. So I think that's a promising direction to do further research. And I think it's although we don't have a conclusive answer here, but I think it's very possible that we can build graph foundation models based on broad categories. Like we may have a graph foundation model for biomedical chemistry domain, or we have a graph foundation model for social network or e-commerce domain, right? So hope that answer your question.
Yes, thank you.
Okay, thank you. So any other question? Okay, I think if there is another question, I think that's the end of this tutorial, and I think we have it's a lunch break. Okay, you can enjoy your lunch. Thank you.